Students, have you ever wondered when you have a HCl molecule, does it exist or does it have the covalent properties? Because it does have a covalent bond within it, but it does not. It actually shows a dipolar nature. We have learned about this in our first chapter as well, that is in the chapter of electrostatic forces. So what exactly is a dipole? Dipole is nothing but two charges having equal magnitude but opposite signatures. Therefore, there is always a force of attraction between them. But they are separated by a certain distance, and that combination consists for us or tells us as to what exactly is a dipole. Let's try to understand about how to find out the potential energy of a dipole when it is present in an external electric field.
So now we move on to find out the electric potential due to an electric dipole. As we already know, what exactly is an electric dipole? Electric dipole is nothing but you need to have two charges. Let's say you have a minus q charge, you have a plus q charge, and these two are separated by distance r, let's say. Okay, so when these two are separated by this particular distance r, so this particular combination is known as an electric dipole. Di means two, pole means two poles, opposite charges. Okay, if you have to find out the electric potential due to them, how exactly we are going to do it? So let me explain that. If you remember, we had discussed about the electric field due to an electric dipole. So in a similar manner, we can talk about the electric potential due to an electric dipole. So there are two combinations that we are going to take, then we are going to come to the general combination. So let's say I have minus q charge, I have plus q charge. So if I talk about in an axial plane, so in the case of an actual plane, so what exactly I'm going to do? So if I say the distance between them is equals to 2d, okay, and from the center of this, let's say from this particular point, if you're trying to find out the potential at a point r, let's say here is a particular point p at which you're trying to find out the potential. So how exactly you're going to do it? So for finding out, since it's going to be just a linear combination, it's just a superposition principle that you're going to follow. So you are going to get k from plus q over is going to be equals to r minus d, mind you. Then from the other one it's going to be minus kq upon r plus d. So you're going to simplify this, so this should give you the answer. So you'll get k if you take it out common, so you'll get r plus d minus r plus d over r square minus d square it is. Yeah, so here r and r are going to get cancelled, so you'll get k q into 2d over r square minus d square. Now since the distance between these two is 2d and each charge is q, so q times 2d is nothing but the dipole moment, so you'll get k into p upon r square minus d square, right? So this is due to an axial plane. In a similar way, we can talk about in an equatorial plane. So I'll just give you a hint. So in the case of an equatorial plane, what will we have? We'll take the two charges again, minus q plus q, and at this point, let's say this is a point P, which is going to be at this place. This is r. Here, this distance is d. This distance is d. So what you are going to get, this is the point that you will have, this is the distance that you will have, so this is going to be equal to r square plus d square. So you are going to find out the potential due to minus q, and you are going to find out the potential due to plus q. Both the distances are going to be the same, mind you. So here you will get v equals to kq upon square root of r square plus d square minus kq upon r square plus d square with a square root sign, right? So using this, we can find out the value in an equatorial plane. So if we talk about in a generic case, so in a generic case, if you are given these, that is, you are given the angle of orientation, so we'll assume that these angles are nearly the same, this angle and this angle are nearly same. So we'll take from the center, so we'll take a component of P, so this is the component of the dipole moment that we have. So Q into 2A, you know that Q into 2A, that is the dipole moment. So here it's going to be this length, so this should have been A and this should have been A. So using this, you'll find out that you are going to find out the value of the dipole moment. As we found out, for Q equals to P by 2, for equatorial position V equals to 0, and just we found it out. So this is how exactly we are going to find out the dipole moment. So either you take along the equatorial, or you take along the axial position, or you take a generic case. So this is going to be the value for the generic case, and for the other two cases, these are the two values, that is the axial position and the equatorial position, if you approximate basically. Hopefully you understood till this point.
We learned that what exactly is the potential energy of a dipole that is present in an electric field. We know that if you have a dipole that is not really oriented along the direction of the external electric field, it will tend to orient itself. So obviously there is going to be a torque involved. So the amount of torque which makes the object move by an angle d theta results into a work. The work is stored in the form of potential energy. So this was a very important point. Please do take a note of that. So this was the potential energy due to a dipole. We'll move on and try to understand about surfaces which have the same potential.